This presentation is titled Mixed Frequency VAR, Estimation and Application, focusing on bridging the gap between monthly and quarterly data in EViews. It highlights that macroeconomics operates in a mixed frequency world, and our models should reflect that reality. The presentation was prepared by Nyom Kinte Learned Viet Lot. This slide visually presents the core problem we're addressing, the frequency mismatch dilemma. On the left, we see a timeline illustrating how quarterly data, like GDP, provides only 4 data points per year, while monthly data, such as CPI, offers much higher frequency observations. The gaps between the quarterly GDP releases highlight missing information that exists at the monthly level. The dilemma is that standard VAR models, which are foundational for many macroeconomic analyses, require all variables to be at an identical frequency. You can't simply combine monthly inflation with quarterly GDP in a traditional VAR. The common, but flawed, workaround has historically been aggregation. This involves averaging or summing high-frequency data, like monthly CPI, to convert it to a lower frequency, like quarterly CPI. However, as the right side of the slide titled The Cost of Aggregation emphasizes, this method discards vital variance information and critically delays signal detection. By converting monthly data to quarterly averages, you lose all insight into the intra-quarter dynamics. For example, if monthly inflation was 0.1% in January, 0.2% in February, and 0.8% in March, the quarterly average would hide this accelerating trend. Aggregation treats this the same as a quarter where inflation was 0.8%, 0.2%, and 0.1%, a decelerating trend. This loss of information means we miss crucial turning points in the economy. This is why we need a bridge, not a filter, a way to integrate these different frequencies without sacrificing valuable data. This leads us to a decision point. When faced with mixed frequency data, what are our modeling options? Let's look at a flowchart to guide our choice. This flowchart provides a roadmap for choosing the right model. We start with multivariate time series data. The first question is always, are the frequencies the same? If yes, and the data is stationary, a standard VAR is appropriate. If the data is non-stationary but co-integrated, you'd use a VECM. If the frequencies are different, we enter the realm of MVAR. Here, a key consideration is the sample size. If you have a large sample size, a high ratio of observations T to parameters K, the U-MIDAS approach is suitable. However, if your sample size is small, you risk parameter proliferation. In this case, a Bayesian MVAR is preferred because it uses shrinkage to impose some structure on the coefficients, preventing overfitting. The core innovation of U-MIDAS is a clever technique called stacking. Instead of compressing the time dimension by averaging, we expand the variable dimension. We transform a time dimension problem into a variable dimension problem. This allows the model to assign different weights to the first, second, or third month of the quarter, as shown in the equation YQ equals C plus B1 times XM1 plus B2 times XM2 plus B3 times XM3 plus E. This means we treat each month as a separate variable rather than averaging them. First, just like a standard VAR, the MFVAR model requires all data to be stationary. You must perform unit root tests and difference the data if necessary before estimation. Second, be mindful of parameter proliferation. Because we are creating new variables through stacking, the number of coefficients to estimate explodes. A simple bivariate VAR with one lag, mixing monthly and quarterly data, will estimate 3 times more coefficients than a standard VAR. This leads to a data constraint. The dependent variable must be the low-frequency variable, e.g. quarterly GDP, and the independent variables must be the high-frequency ones, e.g. monthly inflation. Finally, from a practical standpoint, we're focusing on EViews, which has built-in support for both U-MIDAS and Bayesian MFVAR, making these advanced techniques accessible. MFVAR captures more detail, but consumes degrees of freedom. If you have a model with 2 quarterly variables and 3 monthly variables, the number of parameters can quickly become larger than your number of observations, T, especially with a few lags. This is why ensuring your sample size is sufficient for the number of parameters, K, is a critical trade-off.
This is perhaps the most important practical step. You cannot run an MFVAR in EViews if you paste all your data onto a single page, for example, a quarterly workfile page. The correct approach is to use a multi-page workfile. You must create separate pages for each frequency. For our example, we would have one page for quarterly data and another for monthly data. The golden rule is simple: one page, one frequency. This structure allows EViews to understand the native frequency of each series before it performs the stacking procedure internally. All estimations are then initiated from the low-frequency page. In our case, we would be working on the quarterly page when we tell EViews to estimate the VAR. You would create a new EViews workfile. The first page might be named Quarterly and have a start date of 1980 Q1. Then you would add a new page, name it Monthly, and set its frequency with a start date of 1980 M1. You then paste your GDP data into the first page and your CPI data into the second. Let's see this in action with a real-world case study, replicating a well-known paper by Giesels.
To demonstrate the process, we will replicate a study by Giesels from 2016 using a dataset called cansfed.werf1, which is included with EViews. This ensures our results can be verified against academic literature. As you can see in the screenshot, the workfile is correctly structured. There is a quarterly page containing the GDP series. There is also a monthly page containing 3 high-frequency variables: industrial production, IP, inflation, INFL, and unemployment, UNMP. Before proceeding, we would perform a data checklist, ensure pages are named correctly, date ranges are aligned, and, most importantly, all series have been tested for and transformed to stationarity. We use this real-world data to verify that the software output matches established academic literature. For this dataset, the variables are likely already prepared and differenced to ensure stationarity. Always check the documentation or perform your own unit root tests first. With our data properly set up in the multi-page workfile, we can now initiate the estimation process in EViews. To begin, you navigate to Quick in the main menu and select Estimate VAR. This opens the VAR specification dialog box. The crucial step here is to change the VAR type. By default, it's set to Unrestricted VAR. You must select the Mixed Frequency radio button. Notice how the interface changes dynamically. As soon as you select Mixed Frequency, a new input field labeled High Frequency Variables appears at the bottom. This is where we will specify our monthly regressors. The endogenous variables will be our low-frequency variables, and we'll specify the lag intervals just as we would for a standard VAR. To reference a variable from another page in the workfile, EViews uses a simple but powerful syntax: the page name, followed by a backslash, followed by the variable name. So, to include the industrial production series, which is on the monthly page, we would type monthly IP. We list all our high-frequency variables in the high-frequency variables box, separated by spaces. This tells EViews to pull this data from the monthly page and stack it appropriately for the estimation. This method is very efficient because it doesn't require you to physically copy and paste or merge data. EViews handles the alignment and stacking behind the scenes based on the dates in each page. As shown in the image, we would enter GDP as the endogenous variable. In the high-frequency box, we would enter monthly IP, monthly inflation, monthly unemp to include all 3 of our monthly indicators. With the variable specified, the final step before estimation is to configure the model's hyperparameters. After setting up the variables, we click on the Hyperparameters tab. Here, we can select the estimation type. We'll stick with U-MIDAS. This is also where you would select the Bayesian option if you had a small sample size. The frequency conversion parameter is automatically set. Since we are mixing monthly and quarterly data, EViews correctly defaults this to 3, as there are 3 months in a quarter. You can also specify the number of lags for the high-frequency variables here. This is distinct from the lags of the endogenous variable we set earlier. The output table for an MFVAR looks different from a standard regression. Notice the variable names: IP sub 01, IP sub 02, and IP sub 03.
These suffixes correspond to the timing within the low-frequency period. IP sub 01 is the coefficient for industrial production from the first month of the quarter. IP sub 02 is for the second month, and IP sub 03 is for the third month. This is the payoff for using the stacking method. We can now test hypotheses about the timing of effects. In this output, we can see that the coefficient for IP sub 03 is negative 0.198 and is statistically significant, with a t-statistic of negative 2.538. This result suggests that a shock to industrial production in the third month of the quarter has a significant negative impact on GDP, while shocks in the first 2 months do not have a statistically significant effect. Looking at the table, the coefficient for IP sub 01 is 0.009, with a t-statistic of 0.191, which is not significant. In contrast, the coefficient for IP sub 03 is negative 0.198, with a t-statistic of negative 2.538, which is significant at the 5% level. This is a clear demonstration of intra-quarter dynamics. Beyond individual coefficients, one of the most powerful tools in VAR analysis is understanding how shocks propagate through the system over time. This brings us to impulse response analysis.
Impulse response functions, or IRFs, are especially insightful in an MFVAR context. They allow us to see how high-frequency noise propagates into low-frequency structural trends. For example, how a shock in monthly inflation impacts quarterly GDP over time. To view these in EViews, simply go to View and then select Impulse Response after estimating your MFVAR object. The killer app for mixed frequency VAR models is nowcasting. This refers to the prediction of the very recent past, the present, and the very near future. The problem is that low-frequency data, like GDP, is released with a significant lag. By the time we get Q1 GDP data, we are already well into Q2. Nowcasting uses the high-frequency data that is already available for the current quarter to predict the low-frequency variable before its official release. For example, we can use January and February inflation and employment data to predict Q1 GDP in early March, as illustrated by the fan chart on the left. This is incredibly valuable for real-time policy analysis and decision-making, as it provides a timely snapshot of the economy. In EViews, this is done through the Proc Forecast menu. Imagine it's March 15th. The government has released inflation data for January and February. Using a nowcasting model, an analyst can generate a prediction for Q1 GDP, complete with a confidence interval, the fan chart, long before the official statistics are published in late April. After estimation, you should always check for issues like serial correlation in the residuals, using tests like the Lagrange multiplier, or LM test. A particularly critical check for any VAR model is stability. Because MFVAR models estimate so many parameters, the risk of instability is higher. A stable VAR is one where the effects of shocks die out over time. We check this by examining the inverse roots of the characteristic AR polynomial. For the model to be stable, all roots must lie inside the unit circle, as shown in the plot. If any root is outside the circle, the model is explosive, and the impulse responses are not meaningful. If your model is unstable, the first thing to check is your data stationarity. If that's correct, the instability is likely due to overfitting from too many parameters. The recommended solution is to switch to a Bayesian MFVAR, which uses shrinkage to impose stability. If you estimate a model and find one of the blue dots in the stability graph is outside the red unit circle, your forecasts and impulse responses will be unreliable, often showing effects that grow infinitely. This is a clear signal to re-specify your model, perhaps by reducing lags or using the Bayesian approach. For those who prefer working with code over menus, EViews offers a powerful command line syntax for MFVAR. For power users, or for tasks that need to be repeated, like in a rolling forecast, using the command line is much faster than the graphical user interface. You first declare a VAR object. Let's call it MFVAR object. Then you use the .ls command to estimate it. The key is the option t equals mixed, which tells EViews to perform a mixed frequency estimation. The syntax for specifying variables is a bit different. You list the low frequency variable, then @, then the high frequency page in variables. For example,
GDP at monthly/IP/monthly/infla. After estimation, you can easily generate impulse responses and forecasts by calling the .impulse and .forecast methods on your estimated VAR object. To further explore this topic, here are some key references. The first is a paper by Geisels from 2016, titled Macroeconomics and the Reality of Mixed Frequency Data, published in the Journal of Econometrics. We also have a paper by Shorefide and Song from 2013 on real-time forecasting with a mixed frequency VAR. For practical guidance within EViews, refer to the EViews User Guide 2, specifically the section on Multiple Equation Analysis, Mixed Frequency VAR. Additionally, for a full mathematical derivation of the mixed frequency VAR, you can refer to the EViews help topic on mixed frequency VAR. The cansfed.wf1 example file, which we used in our demonstration, is readily available in the EViews examples folder, allowing you to replicate our steps and explore